we have to vaporize the solid substance either by giving heat directly or by other means, that means by laser or by an electron beam or by sputtering. This is the sputtering is the evaporation uh, without temperature. Evaporation, what do you mean by evaporation? Evaporation means make the elements apart. To make the atoms, not elements, to make the atoms apart. When they are solid when they are in touch with each other. They will be liquid when they are not in touch with each other, but they have an attraction between them, then it is liquid. But if they are far apart, so that there is no attraction between two atoms, then, or there is no attraction between two molecules, then it is called a vapor. Now, generally, we do it by giving your temperature or heat. We we basically break the bond by which they are attached here. We break the bond means interatomic or intermolecular bond, not the ionic bond or covalent bond. We cannot break the ionic or covalent bond by simple heating. So we actually, what we do, we break the intermolecular bond. Say, for example, in case of water, water becomes vapor at 100 degrees centigrade. What we do there, we break the hydrogen bond between two water molecules such that two water molecules are far apart so that there is no attraction between the two water molecules. So this vaporization is done by giving heat by any way. Say if you give heat by electron beam, or you can give heat by laser deposition, or by laser. And sputtering is another technique for evaporation. How we do that? We just give energy from an atom, or we just give energy by the bombardment of atom to the surface, and the molecule will come out from the surface. That is also evaporation. So the main principle of the physical vapor deposition is to vaporize a solid substance and then condense it onto a substrate. This is the main principle of physical vapor deposition. So we have seen the direct evaporation method. We have seen the electron beam evaporation method. We have seen the pulsed laser evaporation method, and we have also seen partially the sputtering method. Now we'll see the sputtering method more details. So here we told you that this is the beam of ion that bombards, that strikes on a surface of a target material, of which we want to make a thin film. So when it strikes on that surface, the atoms of that surface or the molecules of that surface will go out like that, and it will condense on a substrate to get a thin film. Now, This is the, I told you, and I have shown a video of this to you. I told you this is the main principal source, and it is evaporation to gas phase and transported to again to deposit into a substrate. Say, for example, if it is a substrate, we sputter this, we bombard this with a beam of ion, and the molecules or atoms of that target will come out by that bombardment or by that sputtering, and it will condense on this substrate and we'll get the thin film. Now, what are the requirements? What are the requirements for this sputtering method? The first requirement is the vacuum. We should have vacuum we should have a vacuum chamber, because if we don't have vacuum, then two things can happen. One is the contamination can happen, and second is the collision of your target molecule with the air molecule. Collision happens from of target molecule with air molecule. So the vacuum is necessary. Second one is inert gas is necessary. Why inert gas is necessary? To sputter, to bombard the surface of the target material, inert gas is necessary. Then we require power supply to bombard or to sputter the target material, and the sputtering gas also required. Now, what are the steps? Now, how to sputter? Ions are generated and directed to a target. So, we have to bombard or sputter the target by the ions, not by the atoms or molecules. Now, why? Why we require ions to bombard or sputter a target material? Generally, argon ion is used. It is because if it is argon molecule, you know, to bombard this in this surface, we have to give this molecule or ions, whatever it may be, we have to give this substance energy. We have to give this substance energy. Why? To come here and to strike the molecule, to bombard the molecule or atoms of the substrate and make them free. To break their bond, we have to give the energy to the to this molecule to break the bond in the substrate, break the bond of the atom in the substrate. Now, you see, a molecule or an atom is a very small substance. It is very light. So how can one give energy to the atom or molecule? It is very difficult to give energy towards to an atom or molecule because it is very light. You can consider a cotton. Say, for example, a smaller amount of cotton. I'm telling you that I tell you to throw your cotton You cannot do it. It will not go that distance, that much distance. If it is a stone, as heavy substance, it will go far away. But the cotton substance, because it is light, it will not go that far. So a molecule or an atom, it is not easy to give energy to a molecule or an atom. So we use the ion. What is the advantage of the ion? Say, for example, it is positively charged ion, and we made this substrate negatively charged. We made this target negatively charged. Then what will happen? It will, the negative charge will attract the positive charge, and this positive charge will get energy automatically to strike this target material. So the ions are required to strike, to bombard the target material. We know the collection of ions are known as plasma. If there is a collection of many collection of ions, so we call that plasma. Plasma means a mixture of ion, basically a mixture of ion and electron and some unreacted atom or molecule. So this is plasma. So you can strike this target material by a plasma of argon. Why argon? Because argon will not react with the target material, because argon is an inert gas. It will not react with the target material. So we use argon to strike the target material. So ions are generated. First, ions are produced and directed at a target, and these ions are directed at a target. The ions sputter target atoms. The ions will hit the target atoms, and then some of the target atoms will be ejected by the sputtering. The ejected atoms are transported to the substance, then substrate. Then these atoms will go to the substrate, and atom condense and form a thin film. And the atoms will condense here to form a thin film. This is the simple step of sputtering. Now, how sputtering deposition film growth? How a sputter deposited the film growth? Sputtered atoms have velocities about 3 to 6 into 10 to the power 5 centimeter per second. These have velocities. The sputtered atoms, these sputtered atoms initially have velocity of 3 to 6 into 10 to the power 5 centimeter per second, and the energy of 10 to 40 electron volt. It is generally the sputtered atoms comes from here. Many of these atoms deposited upon the surface. Not all the sputtered atoms, excuse me. Hello. Sorry. Now, many of these atoms deposited upon the surface. Not all the sputtered atom will deposit it on the substrate. Some will go here and there, and some will suffer collision with the argon atom. Here argon ion will come, and some sputter atom will collide with the argon ion, and some sputter atom collide with themselves. Some sputter atom collide with the gases remains here, and some sputtered atom will go here and there. But many of the sputtered atom will go to the substrate to form the thin film. Thus, the sputtered atoms will suffer one or more collision with the sputter gas. Sputter gas means argon, the plasma of the argon. This is the sputter gas. So some sputter atom will make a collision to the sputtered gas. Now, when the sputtered atom comes to the substrate here, when this sputtered atom initially have the energy of 10 to 40 electron volt. When it comes here, the energy of this sputtered atom will be reduced to 1 to 2 electron volt due to the traveling or due to the collision or due to various factors. The sputter atoms have arrived at the surface with the reduced energy about 1 to 2 electron volt. And there is a possibility of backscattering to the target That means there is some possibility of this sputtered atoms. There is some possibility of this sputtered atom to hit this argon gas and becomes to and to back to its original position. That means to the target again. The sputtering gas pressure can impact on film deposition parameters such as deposition rate and composition of the film. What is the sputtering gas pressure? That means the pressure of argon plasma. The sputtering gas is the argon plasma. The sputtering gas pressure can impact on the film deposition parameters. That means on the sputtering pressure, the thin film deposition will the thin film deposition will depend on the sputtering gas pressure. That means deposition rate and composition of the film. That means the deposition rate, the rate of deposition will depend on the sputtering gas pressure, and the composition of the film also will depend on the pressure of the sputtering gas. Now, at the first stage, the atoms or elements, whatever it may be, the atoms or molecules, whatever it may be, comes to the substrate like that. It is condensed to the substrate like that. Now, these atoms will act as a center or will act as a nucleus to the film. That means other atoms which are coming will sit or will condense around these atoms, will condense around this atom, will condense around this atom. So the first deposition The first deposition of atoms are the nucleus of that film, of that thin film. You see here, first nucleation occurs. This is the nucleation, and this nuclei will grow larger by condensing the other atoms by the side of it, by the side of it, and this nucleus then coalesce. Coalesce means it joins with one another. It joins with one another. This is coalescing. That means coagulating. It joins in one another and forms the film. These are the defects of the film. These are the defects of the film. Here, the atoms are not condensed there. These are the defects of the film. This is a very small place. So, so with this defect, you can use the thin film. But these are the defects of the film. So the sputtering yield. What is the sputtering yield? Defined as the number of atoms ejected per incident ion. We have bombarded an ion to the target material, and how many number of atoms ejected with that bombardment of ion is known as sputtering yield. This sputtering yield determines the rate of deposition. That means as the sputtering yield increases, deposition rate also increases. And the deposition rate also depends on mass of the bombarding ions. That means mass of the plasma. We generally use argon plasma. Energy of the bombarding ion, how much energy has that plasma, and direction of the incidence, whether it is bombarding by this way or by this way or by this way, in which direction it is bombarding, and the pressure I have told you, the incident gas pressure. So we'll see in short how it is it affects first mass and size of the atom. You see, this is the mass of the projectile, and this is the sputtering yield. First, the mass of the projectile. As the mass of the projectile increases, the sputtering yield also increases. But after some time, uh, 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 as the mass of the projectile increases, sputtering remains constant. So it depends. The sputtering it depends on the mass of the projectile up to some extent. After that, it does not depend on the mass of the projectile. So this is the graph for the gold target. If you sputter the gold atom, then this is the graph of the gold target. And this graph for other targets also, this graph will be more or less similar. So what we see here, the mass of the the sputtering yield depends on the mass of the projectile to some extent, but not always. After that, the sputtering yield remains constant, whether you have increased the mass of the projectile or not. So second one is the ion energy and sputter yield. You see from the graph, this is a sputtering yield and this is ion energy. Below some energy, say for example, this is 10 to the power, say 1.5. Say for example, it is 10 to the power 1.5. Below 10 to the power 1.5, no sputtering yield occurs. No sputtering yield occurs. After 10 to the power 1.5, the sputtering yield increases. The sputtering yield increases as the ion energy increases. But after certain time, or after some energy, after a certain energy, it will decrease again. So there is a threshold energy for sputtering, below which sputtering will not occur. And if you increase the ion energy very much, if you increase it too much, then sputtering it will decrease again. There is a optimum energy for sputtering yield, optimum ion energy for sputtering yield. After that, the sputtering yield will decrease. Now the direction. You see, if the direction is this way, if the direction is this way, then the sputtered molecule can go inside the target material. It will not sputter from the surface. The sputtering molecule, the sputtering gas will go directly inside the surface material, and when it will go inside the surface material, it will sputter, it will give its energy to the to inside material, to inner material, which cannot sputter an atom from this from the surface. So you have to you have to sputter on this by the angle 45 degree. You have to sputter this by the angle 45 degree. If you sputter by the angle 45 degree, then the surface atoms will come out and go to the substrate. If you sputter in this way, it will go inside the material, and the surface atom will not come out. The inside material, the inside atom will get the energy, which will not free any surface atom. So this is the direction and the pressure. If you reduce the pressure, that means pressure reduction allow better deposited atoms. Pressure reduction allow better deposited atom. That means if you reduce the pressure of that chamber, that means this chamber, if you reduce the pressure of this chamber, then there will be a better deposition. Now, how you can reduce the pressure of this chamber? You can reduce the pressure of this chamber by maintaining vacuum here. That means you have to add a vacuum machine. You have to add a vacuum machine here to make vacuum here, so that the pressure is reduced. Then what will happen if when the pressure is reduced? What will happen? The mean free path of this surface atom will increase, and it will go to the substrate to form a film growth. So it depends on the pressure also. Now, there are different types of sputtering method. One is reactive or non-reactive sputtering, RF and DC sputtering, magnetron sputtering, collimated sputtering, ion beam sputtering. Reactive and non-reactive sputtering means if the atoms that is sputtered will react some substance during the traveling towards the substrate molecule. If it reacts with some substance, say for example, you have a target material of aluminum and you have sputtered the aluminum atom. It reacts with oxygen atom on its travel towards the substrate. Then it will called reactive sputtering. Sometimes it requires, say for example, you want to have a film of aluminum oxide. Then what will happen? You will insert oxygen gas in the chamber, and the aluminum atom, during traveling towards the substrate, it will react with oxygen atom to form aluminum oxide, and the substrate will get aluminum oxide molecule instead of aluminum. And non-reactive means if you don't want that reaction, then you will make vacuum to the chamber. And RF and DC sputtering means radio frequency, and direct current sputtering means the power supply is of radio frequency or direct current, whatever it may be. It may be magnetron, it may be collimated. Collimated means it is directed, and some ion beam sputtering, that means plasma sputtering. This is the sputtering method of your physical vapor deposition. Now, do you have any question regarding a sputtering method? Do you have any question regarding the sputtering method?
সাবস্টেন্স ডিপোজিট হওয়ার পরে স্যার আবার সেটাকে স্যার রিমুভ করে দেওয়ার কি কোনো প্রবাবিলিটি থাকতে পারে যে মলিকুল গিয়ে ডিপোজিট হচ্ছে?
No, it cannot be removed. It cannot be removed, or it will not removed, because it is deposited here and it will not remove from that your substrate, because we do not actually make a thin film to make a thin film only. This thin film will do some work. This thin film will say for example, we can make a transistor with this thin film, or we can make your what we call that inside the computer, what do you call it?
Motherboard or IC?
IC. We want to make an IC with that thin film. So it is this substrate, it is attached to the substrate. It will be attached to the substrate, and the substrate generally is like that, who will catch your atoms, who will catch the atoms. The substrate is like that. You cannot use a substrate as your wish. The substrate is like that. The molecule, when it will come here, it will tightly attached with that substrate. So it cannot be what you call removed, unless and until some chemical process occurs. If you want to clean the substrate by removing that with some chemical, then it will be removed. But normally it cannot be removed. Any other question? Do you have any other question? Okay. Now we will go to the chemical vapor deposition. There is one more what process of physical vapor deposition. We'll see it later. But
স্পাটারিং নিয়ে তো স্যার বইয়ে তেমন কিছু নাই স্যার, মানে একটা বইয়ে মনে হয় স্যার এক পেজ আছে স্যার।
আচ্ছা, আমি দেখবো এটা। আর এখানের মধ্যে তোমার যে এটা দেখা যাচ্ছে স্লাইড গুলো, স্লাইডেই অনেক কিছু আছে স্পাটারিং। হ্যাঁ, এটা ডিটেল স্লাইড, দেয়ার ডিটেল স্লাইড। Okay. Now, next one is chemical vapor deposition. Chemical vapor deposition. By the name, you can understand that there are some reactions occurs here in chemical vapor deposition. That was the physical vapor deposition. There was no reaction there in that physical vapor deposition. But in chemical vapor deposition, you will get some reactions. So what is a chemical vapor deposition, or CVD? What is a chemical vapor deposition? You see, chemical vapor deposition is a process whereby a solid material is deposited from a vapor by a chemical reaction occurring on or in the vicinity of a normally heated substrate. So, what does this mean? You have a substrate. First, you have a substrate. Now, what is called? It is normally heated substrate. That means you have a substrate and you have to heat the substrate. Okay. Now, the material, a solid material is deposited. Solid material is deposited on the substrate from a vapor by a chemical reaction. From a vapor, just like the previous one, from a vapor, but the vapor will react on the substance, on the substrate, or on the vicinity of the substrate. That means near to the substrate. What does it mean? You will pass some gas on the chamber, and these gases will react with each other on the substrate or on the vicinity of the substrate to get a film of reacted substance or to get a film of product. So there is a chemical reaction. There is a chemical reaction in the vapor phase or on the substrate. There will be a chemical reaction. So chemical vapor deposition is a process whereby a solid material is deposited. Okay, that is fine. From a vapor. Okay, that is also fine. But by a chemical reaction occurring on or on the vicinity of normally heated substrate. You have a heated substrate, and on that substrate, some chemical vapor comes, some vapor comes, not chemical vapor, some vapor comes, and they will react on the surface of the substrate or on the vicinity of the substance near to the substrate. And the product, whatever it may be, and the product will deposit it on the substrate. As because there is a chemical reaction occurs, so it is called chemical vapor deposition. As because there is a chemical reaction occurs in the vapor phase, so it is called chemical vapor deposition. The solid material, that means the product which is deposited on the substrate is obtained as a coating, a powder, or a single crystal. The thin films actually, all the thin films actually are of single crystal, as because they are thin, so they are arranged. What do you mean by crystal? Crystal means an they are a arranged substance, arranged three-dimensional substance. As because they are with small amount of molecule, the thickness of the thin film is very small. It is in nanometer or your micrometer level. So the thin film that is formed is actually all the time, almost all the time, it is single crystal. Now you can get this get the film as coating or a powder also. Now, by varying the experimental conditions, what are the experimental conditions? Experimental conditions means the substrate metal. By varying the substrate metal, you can use different type of substrate material. You can use glass, you can use silicon wafer, you can use some nitrides, different types of substrate material you can use. Substrate temperature, the temperature of the substrate, the composition of the reaction gas mixture. What are the reaction gases? They will react. The composition of reaction gas mixture, total pressure of the gas flow, etc. Materials with different properties can be grown. Different types of thin films can be grown. CPT is an example for solid vapor reaction that we will see later. First, what are the main components of CVD equipment? If I can draw something, আমি একটু draw করি তাহলে দেখা যাচ্ছে ঠিক মতো?
স্যার
ওই উল্টা হচ্ছে না তো লেখা?
না স্যার।
ঠিক আছে লেখা?
হ্যাঁ স্যার।
So let us suppose this is a reaction chamber. You have an inlet here, you'll have an inlet here, and there is an outlet also here. There is an outlet also here. So this is a base. It is called susceptor. On this base, a substrate is placed. So a substrate is placed on this base. This is a substrate. This is a substrate. So this chamber is known as reactor. This chamber is known as reactor. Now you flow a mixture of gas here. You will flow a mixture of gas here. Oh, this susceptor actually is made of, say, graphite or stainless steel, SS. This susceptor is made of graphite or stainless steel, and this substrate, you can take this substrate as say as silicon substrate. You can take a silicon wafer, or you can take a glass substrate, whatever it may be, whatever it is suitable for you. This is a substrate. Now, there are some heating arrangement here. Say, for example, here some heating arrangement. There are some heating arrangement here. There are two types of heating arrangements. There are some heating arrangements here. And say, for example, there is a outlet for vacuum. This is a line for vacuum, to make a vacuum. Now, what will happen? The gas flow will come here. The gases will come here, and the substrate is heated here, and the gas will come on that substrate. The gas will condensed on the substrate, will be condensed on that substrate, and they make a reaction here and form a thin film here. Form a, say, this type of thin film here, and then what will happen? In this way, the byproduct of this thin film, of this reaction, and the rest of the gases will go out in this way. Will go out in this way. Now, let us consider a real picture. What is the real picture? Say, for example, you are trying to prepare a thin film of gallium arsenide. You are trying to prepare a thin film of gallium arsenide. Now, what will you do? Gallium arsenide. Now, to prepare the thin film of gallium arsenide, you have to first take the precursor. Gallium, you took the precursor as gallium chloride. Here it is gallium chloride. Generally, what will it be? Gallium chloride will be JaCl2 or JaCl3. What it will be? I think it is 3, or I think it is 3. Okay.
Yes, sir. 3, sir.
Okay. Thank you. So you have to pass this gas. You have to pass gallium chloride gas to the chamber, to the reactor. Let me draw this again. This is the chamber. Let me draw this again. This is the chamber. This is the chamber. And this is the outlet. Say, this is with vacuum. This is with vacuum. And from here, say if I no, we use not, it is not gallium chloride, it's actually, it will be arsenic chloride, and gallium will be here. Gallium will be here. This is gallium. And here you will find the substrate. Here you will find the substrate. Sorry, this is the susceptor. And this is the substrate onto which the film will be formed. Now, hydrogen gas will pass hydrogen gas through this way. Will pass hydrogen gas through this way, and you will find arsenic chloride vapor here. How you'll find arsenic vapor here? Because you know, with every liquid, they are in equilibrium with its vapor. Do you know that?
Yes, sir.
Every liquid, they are in equilibrium with its vapor in a say in a your this what is called in a
Liquid.
not liquid. Say for example, you keep it in a beaker, huh? In a substrate or in a container rather. If you place a liquid in a container, it always will be in equilibrium with its vapor. So if it is arsenic chloride liquid, there must be some arsenic chloride vapor here. How much of arsenic chloride vapor will be here? It will depend on the temperature. If the temperature is high, then the amount of vapor will be higher here. If the temperature is low, the amount of vapor will be low. Now, you will get some arsenic vapor here. And you have passed hydrogen gas through this way. This hydrogen gas will carry the arsenic chloride vapor here and will enter into the reaction chamber. Have you understand? This hydrogen gas will carry the arsenic chloride vapor from here, and this both the arsenic chloride and hydrogen hydrogen gas will enter into the reaction chamber. Now, in that reaction chamber, there are some heating elements here. There are some heating elements here. In that reaction chamber, there are some heating elements here. And here what happens, this arsenic chloride will react with hydrogen, to form arsenic and HCl. On the reactor, this arsenic chloride will react with hydrogen to form arsenic and HCl. This arsenic is also is in the gaseous form, HCl is the also in gaseous form. Now, here you see, here gallium, it is heated. Say, for example, here the temperature is 1000 degrees centigrade. Gallium is heated here. Now, this gallium vapor will react with HCl to form gallium chloride plus hydrogen. Gallium chloride plus hydrogen. Now here what happens? You see, in this chamber now, now many your precursors or many chemicals are in the vapor phase. What are the chemicals? You will get hydrochloric acid, you will get arsenic, you will get gallium vapor, you will get gallium chloride, you will get some arsenic chloride also, that is non-reacted arsenic chloride, many things. But you will find this gallium chloride and arsenic, they are the main chemicals, main gaseous chemicals here. These two will condense here. These two will condense here. Where this is the substrate, this is the substrate where thin film will grow. And here the temperature is say for example 700 degree centigrade. So basically it is a two-zone furnace where in one zone the temperature is 1000 degrees centigrade, and in the other zone the temperature is 700 degrees centigrade. So there is a temperature gradient here. There is a difference of temperature in these two regions. If there is a difference in temperature in these two regions, there some deposition will occur here. Now, what will be that deposition? Arsenic plus gallium chloride, and it will react with hydrogen to form gallium arsenide and HCl. Arsenic, gallium chloride, hydrogen on the substrate, arsenic, gallium chloride, and hydrogen will react with each other to form gallium arsenide and HCl. So we'll get a thin film of gallium arsenide here. We'll get a thin film of gallium arsenide here. And the HCl, this HCl and other gaseous substances which are not deposited here will go out through this way, will go out through this way, and it will be discarded. So hydrochloric acid, unreacted hydrogen, unreacted arsenic chloride, unreacted everything will go out through this way, and you will get some thin film of gallium arsenide here. You will get some thin film of gallium arsenide here. This is the chemical vapor deposition process. This is the chemical vapor deposition process, actually. Do you have any question? Do you have any question? Okay, we'll go to the details of the chemical vapor deposition.
So susceptorটা কি জিনিস স্যার?
Susceptor what you will call is a base, where upon which the substrate is placed. Susceptor is a base upon which substrate is placed. It is the substrate. You cannot place a substrate on the wall of the reactor. It is a base on which your uh, mm, your substrate will be placed. The susceptor is made of graphite or stainless steel, whatever it is. Now I have to change the camera. Now main components of CVD equipment. The role of this first one is chemical vapor precursor supply system. What are the chemical vapor precursor supply system? The chemical vapor precursor supply system means your hydrogen gas, your if I this camera again. তোমরা এটা দেখতে পাচ্ছ স্লাইডটা?
হ্যাঁ স্যার।
আর এটা দেখতে পাচ্ছ আমার লেখাটা? লেখাটা দেখা যাচ্ছে? হ্যাঁ, ওকে, ভেরি গুড। So the role of chemical vapor precursor supply system. What are the vapor precursor? You see the this is here. From here you will get arsenic chloride. This is a vapor, and to bring the arsenic chloride to the reactor, you require hydrogen, and it is a reactant also. Arsenic chloride, it reacts with hydrogen to form arsenic plus HCl. So these are the precursors. Say for example gallium vapor, it is also a precursor. So the role of this component to generate vapor precursor and then deliver to the reactor. That means to generate vapor precursor and then deliver to the reactor. Not always you will find that something will be in the it will be a 2-zone furnace and something will be here as a precursor. Say for example you want to make a silicon your thin film. Then what will you do? You just take silicon silane. You just take silane, and you have a silane vapor here, and hydrogen will take the silane, or something, some gas will take the silane into the your reactor, and there this silane will be cracked. That means the bond of silicon and hydrogen will be break down, and silicon will go to the substrate, and it will make a silicon your thin film. So not always a precursor will be in the reactor. Sometimes, sometimes the one of the precursor will be inside the reactor, and sometimes it may not. But what is told? The role of the component is to generate vapor precursor, then deliver to the reactor. That means first step is to generate the vapor and to deliver it here. Now, the design of the CVD reactor depends on whether the starting material is solid, liquid, or gas. If you see here, the starting material here, it is liquid. The starting material here, it is liquid. And the starting material, this is gas. So there is no solid starting material here. But it may happen sometime. It may happen sometimes. There will be some solid starting material. Then the design of the reactor will be different. Now you see here we have a two-zone temperature reactor. It is one design. You will have a two-zone temperature reactor. One is for gallium and one is for your substrate. It may happen that it is one zone temperature reactor, or it may something else. So the design of this reactor will depend on the physical condition of your precursor, whether it is solid or liquid or gas. The sublimation of a solid precursor depend on surface area of the solid and the contact time. If it is a solid precursor, then you have to sublime the solid precursor because you want your precursor in the gaseous form. So this sublimation will depend actually on the surface area of the solid. Say, for example, if the solid is the surface area like that, the sublimation property, or if the solid is like that, the sublimation property will be different, because the surface area here it is high and here the surface area is small. So the sublimation will be different. The liquid sources often use a bubbler to vaporize the reactants. You see here, this is called a bubbler. You will pass hydrogen here, and it will take the vapor of arsenic chloride from here to here. So this type of thing is bubbler. And a carrier gas, which is a reactive gas or inert gas such as argon. Say, for example, this is a carrier gas which carries the arsenic chloride vapor to the reactor. This is carrier gas. Now, here hydrogen is the reactive gas. Why reactive gas? Because hydrogen carries the arsenic chloride to the chamber and it reacts with arsenic chloride to form arsenic and HCl. So it is a reactive gas also. It is a carrier and the reactive gas both. But in some cases, the carrier gas may not be reactive, may not react, will not require to react, but it have to carry. This gas will have to carry. So then we use argon as a carrier gas. Then we use argon as a carrier gas. So reactive gases such as hydrogen or inert gas such as argon to transport the vaporized reactants into the reactor. To transport the vaporized reactant into the reactor. So a carrier gas is required to transport the gas to the reactor. Do you have any question on that? Now, I have a question. Why a carrier gas is required? Why a carrier gas is required? Why hydrogen should come here and carry the gallium arsenic chloride gas to the chamber? What will happen if I pass hydrogen gas through this way and arsenic chloride gas straight to this way? What is the difference between them? Why a carrier gas requires? Why you have to carry? Why one gas have to carry the arsenic chloride gas to this chamber? It is because you do not have uh, that much amount of arsenic chloride gas. Why you do not have that much amount of arsenic chloride gas? Because arsenic chloride is very much costly. Uh, why it is very costly? Because of its purity. Purity. It is very pure arsenic chloride. It is very pure arsenic chloride. So it is very costly. Say for example, a 10 ml of arsenic chloride, that much pure arsenic chloride requires 10 lakh taka. Now, if you vaporize this 10 lakh taka, if you vaporize this arsenic chloride of 10 lakh taka and make this flow to the chamber, and some arsenic deposited here as gallium arsenide, and most of the arsenic chloride will go out, and you have to destroy this arsenic chloride, it will not be economically feasible for us. So what we will do, some vapor of arsenic chloride is here, and we will carry that vapor of arsenic chloride to the chamber by a carrier gas. So the waste of arsenic chloride is heavily minimized. The waste of arsenic chloride is heavily minimized. I told you in the previous class that the the nanomaterial the nanomaterials or the precursors of the nanomaterials are very much costly. So we have a always we think how to minimize the your loss. How to minimize the loss? You see here, most of the substance will go out. Only some portion of your precursor material will deposit on the substrate as thin film, but most of them will go out. So if we evaporate 10 lakh taka and let this evaporated gas go out from the chamber, then the gallium arsenide thin film will will be highly cost. So we use a carrier gas to carry this small amount of arsenic chloride gas to the reaction chamber. Now, this is a say for example reactor chamber. There are two types of chamber. First chamber is the whole chamber is heated. That is called hot wall reactor. That means the whole reactor is heated. That is called hot wall reactor. So what is the advantage or disadvantage of this hot wall reactor? In the hot wall reactor, uh, the reaction may take place not around this substrate. The reaction may take place in anywhere in the chamber or in the reactor, not around this substance. The the whole chamber is hot. The whole chamber is hot. So the reaction of gallium and arsenic can take place anywhere, and the film can grow anywhere in the in the reactor, inside the reactor. And contamination may also happen, that some other substances can also contaminate the thin film. So it is the disadvantage of a hot wall reactor. We for that we prefer always the cold wall reactor. That means the heating is uh, just the heating is in the region just where it is required. Heating elements are here where it is required. The heating elements are here where it is required, not in all the chamber. But there are some disadvantage also. It is difficult to get a uniform layer of the film. So we have two types of CVD reactors. One is hot wall, and another one is cold wall reactor. Uh, the effluent gas handling system. Effluent gas means the gas which is going out. As because hydrochloric acid, arsenic gas that are going out, so you have to neutralize that hydrochloric acid gas, or that your arsenic gas. You have to do something something with that gases, so that it will not it will not create harm to the environment or somebody. So these are the effluent gas handling system, how to handle your effluent gas that is going out. Now, this is the CVD equipment I have already discussed with you. Say this is the deposition chamber. This is the deposition chamber where deposition occurs, and some gas inlets here, and there is some gas outlet and waste treatment here, and and here some RF power supply means heating is occurred here, heating element is here. So this is a simple CVD equipment. So you see what are the steps involved in the CVD. Transport of the reactants by forced convection to the deposition region. That means transport of the reactants by a carrier gas. That means forced convection means by a carrier gas to the reaction region, deposition region actually. Transport of reactants by diffusion from the main gas stream to the substrate surface. Now, the gases will come from the main gas stream to the substrate surface, and the gas will absorb in the substrate surface, and then chemical reaction occurs on that substrate surface. Chemical decomposition and other surface reaction takes place. And then what happened? Desorption of byproducts from the surface. Here you see the HCl. Here HCl also produced here, but HCl will come out from the substrate. That means desorption of byproduct from the substrate, and transport of this HCl and other byproducts to the convection area from the deposition region. This is the these are the steps that are involved. These are the steps that are involved in the in the chemical vapor deposition process. And this is a slight mechanism I have explained, uh, how a gas phase reaction occurs and how it goes to the substrate. I have explained you. Now the types of chemical vapor deposition. There are 5 types of chemical vapor deposition occurs. One is low pressure chemical vapor deposition. Low pressure chemical vapor deposition means there is a vacuum system attached to that chemical vapor deposition, your this reactor. Another one is metal organic chemical vapor deposition. This means that an organometallic compound is deposited, or an organometallic compound is required there. A photon laser induced chemical vapor deposition, plasma enhanced chemical vapor deposition, and atmospheric pressure chemical vapor deposition. So in the atmospheric pressure chemical vapor deposition, then in the atmospheric pressure chemical vapor deposition, it works at atmospheric pressure. This is the main advantage. It works at atmospheric pressure. So, so we do not require any vacuum system. So if we do not require any vacuum system, it will be very cheap. But it is atmospheric pressure chemical deposition has inherently poor utilization of your precursors, of your starting materials. Most of the starting materials will go out from this reactor, from the reactor. So chemical vapor deposition is cheap, but it will not give you your required amount of thin film. Now the low pressure chemical vapor deposition, you will get a good quality of your thin film by low pressure chemical vapor deposition, but it is a bit costly. Why? Because a vacuum system is required here. So vacuum system, if vacuum system required here, so its cost will be increased. It is the first disadvantage. Second disadvantage is, or advantage, or whatever you will call, the second thing is that the time which is required to form a thin film will be higher, as because it is a low pressure system, the time will be higher to make a thin film, but you will get a pure thin film for this low pressure system. And another thing is, for that low pressure system, you will require slightly higher temperature than a atmospheric pressure CVD. The LP CVD will require some higher temperature. Now, next one is the metal organic chemical vapor deposition. Here, the metal organic compounds are used as molecular precursor. Say, for example, for silicon deposition, if you use tetramethylsilane, then it is a metal organic your precursor. So this is the main disadvantage. Are the precursor tend to be very expensive and are very volatile. This is a very volatile and it is very expensive. So it is one disadvantage, but the advantage is that their high volatility at moderate, at low temperature. You will find that this gas type precursor at a very low temperature. You will require a very low temperature. Then you'll have laser chemical vapor deposition, where you use laser beam to hit the substrate. You will use laser beam to hit the substrate, so that you can hit locally. You can have a cold wall reactor very nicely. You can get a cold wall reactor very nicely, as because it is heated locally. A very good quality of thin film will be deposited. And next one is plasma enhanced chemical vapor deposition. That means you use plasma to decompose a molecule that will not decompose at a reasonable elevated temperature. Say, for example, I told you that arsenic chloride will react with hydrogen to form arsenic. It is a decomposition to get arsenic. But some molecules are there, say, for example, silicon dioxide, silicon nitride, they will not decompose by this reaction, or by some means by heating. So you use plasma to heat that out, to break the bond and to make the silicon out from this substance, from this material. This is the plasma enhanced reactor. So there are some advantages and disadvantages of this type of materials, or of this type of your deposition, and some applications also here. There is nothing to that you can understand if you read it. So this is the chemical vapor deposition technique. Do you have any question? No question. As usual.